This is Neptune, the planet that should not be where it is. 4.5 billion kilometers from the Sun, in a realm of space where sunlight is 900 times fainter than what we experience on Earth, lies a planet. It's not the largest in our solar system, nor the closest, and it certainly isn't the most renowned. Yet, it stands out as perhaps the most paradoxical of them all. Neptune is blue. Not the pale, washed-out hue of a winter sky, but a deep, vibrant azure, the color of something ancient, cold, and still shrouded in mystery. From this distance, the Sun appears as little more than a bright star. High noon on Neptune would feel like the depths of twilight here on Earth. The temperature at its cloud tops plummets to a staggering -218 degrees Celsius, making it one of the coldest atmospheres we can measure in our solar system. And yet, this frozen, dimly lit world is home to the fastest winds ever recorded on any planet. Winds that howl across Neptune's atmosphere at over 2,100 kilometers per hour, faster than the speed of sound on Earth. Winds so ferocious that if they were to exist in our atmosphere, they would obliterate buildings and strip the ground bare. In a place that receives almost no solar energy, where external heat is virtually non-existent to fuel weather systems, the atmosphere rages with a ferocity that defies all explanation. This is the first contradiction. It certainly won't be the last. For Neptune is not merely a cold, blustery world on the fringes of the solar system. It is a planet that defies its very location. According to our best models of solar system formation, Neptune originated billions of kilometers closer to the Sun, somewhere between the orbits of present-day Jupiter and Saturn. It thrived in a warmer, denser environment, feasting on the plentiful materials of the young solar nebula. Then, through a series of gravitational events that reshaped the entire outer solar system, it migrated outward. It barreled through a primordial belt of icy bodies, scattering them in all directions, inward toward the Sun, outward toward the stars, and into the peculiar orbits we observe today. In this process, Neptune obliterated the original Kuiper Belt and forged a new one. It rearranged the very furniture of the solar system. And it did all this quietly, over millions of years, without a single witness. Tonight, we embark on a journey through Neptune's history, from its tumultuous birth in the inner solar system to its current exile at the edge of darkness, from the storms that rage across its surface to the diamond rain that may cascade through its depths, from its pilfered moon to its fractured magnetic field. Because Neptune is not just the eighth planet, it is a chronicle of everything that went awry and everything that went right in the formation of our solar system. And what it reveals about the universe is far stranger than what it conceals. Be sure to subscribe, for there are countless more extraordinary cosmic tales awaiting discovery. For most of human history, the solar system was thought to end at Saturn. The sixth planet, visible to the naked eye as a pale golden wanderer among the stars, marked the edge of the known universe. Beyond it, there was nothing, or so it was believed. The discovery of Uranus in 1781 by William Herschel expanded that boundary for the first time in recorded history, adding a seventh planet to our celestial catalogue. But Uranus presented a conundrum. It did not move as it was expected to. Within decades of its discovery, astronomers began to notice irregularities in Uranus's orbit, small but persistent deviations from the path predicted by Newton's law of universal gravitation. The planet was being tugged. Something massive and unseen was pulling it slightly off course. The discrepancies were minor, yet they were undeniable, and they could not be accounted for by the gravitational influence of Jupiter, Saturn, or any known celestial body. Two possibilities emerged. Either Newton's laws were flawed, or there was another planet lurking out there. In the 1840s, two mathematicians, working independently on either side of the English Channel and completely unaware of each other's efforts, embarked on a quest to uncover a hidden celestial body. In Cambridge, a young British mathematician named John Couch Adams began calculating the position of a hypothetical eighth planet as early as 1843. By 1845, he had arrived at a solution. Meanwhile, in Paris, Urbain Jean-Joseph Le Verrier, spurred on by François Arago, the director of the Paris Observatory, initiated similar calculations during the summer of 1845. By June 1846, Le Verrier had published his predicted coordinates for this elusive planet. What transpired next became one of the most iconic moments in the annals of science, as well as one of its most contentious disputes. Adams shared his findings with James Challis, the director of the Cambridge Observatory, and astronomer Royal George Biddle Airy. Unfortunately, neither took action based on Adams's predictions. The significance of his work went unacknowledged, with his calculations collecting dust, while the unknown planet continued its slow, silent journey through the cosmos. On the other side of the Channel, Le Verrier faced his own challenges in finding someone willing to search for the planet he had predicted. French astronomers showed little interest. Undeterred, Le Verrier reached out to Johann Gottfried Galle at the Berlin Observatory, providing him with the coordinates he had calculated. On the night of September 23, 1846, Galle pointed his telescope to the predicted location. Within an hour, he made the groundbreaking discovery. A faint blue point of light appeared, less than a degree from where Le Verrier had indicated. Neptune had been discovered, not through mere observation or serendipity, but through the power of mathematics. It became the first planet in history to be identified solely through calculation. Le Verrier had, in the words famously attributed to Arago, discovered a planet with the stroke of his pen. Adams, whose prediction was slightly off by about 12 degrees, received partial credit. Yet the dispute over priority between England and France would linger for decades. Adams, however, displayed grace, publicly acknowledging that Le Verrier's work had been published first and had directly contributed to the discovery. The revelation sent ripples through the scientific community and beyond. Newspapers in both London and Paris splashed headlines across their pages. The public was enthralled. Here was tangible proof that the unseen mechanisms of the cosmos could be deciphered through human intellect. A massive, ancient planet had been lurking in plain sight for billions of years, and two men, armed only with pens and paper, had unveiled it without ever peering through a telescope. The discovery of Neptune represented more than just a scientific milestone. It validated Newton's laws of physics in a way that had never been envisioned before. If mathematics could predict the existence and location of a hidden world billions of kilometers away, then the laws of gravity were not mere approximations. They were fundamental truths about the very fabric of the universe. The solar system was not a chaotic array of wandering bodies. It was a coherent system governed by precise laws, where every wobble and deviation contained clues about the hidden. Yet, within this triumph lay a poignant irony. Galileo, the pioneer of telescopic astronomy, had observed Neptune with his modest telescope back in January 1613, more than 2 centuries before Galle's discovery. He had recorded it as a faint star in his notes. Had he continued to observe it for a few more nights, he would have noticed its movement against the backdrop of stars. The first planet discovered through mathematics had been seen and overlooked by the greatest observer of his time. And yet, despite the elegance of its discovery, Neptune remained shrouded in mystery. It was merely a faint blue dot, unimaginably distant, revealing almost nothing even through the most advanced telescopes of the 19th and 20th centuries. Located about 30.1 astronomical units from the Sun, or roughly 4.5 billion kilometers away, light from the Sun took over 4 hours to reach it. Astronomers understood that it was a colossal planet, perhaps 17 times the mass of Earth. They knew it had at least one moon, Triton, which was discovered just 17 days after Neptune itself. They recognized that its atmosphere contained hydrogen, helium, and methane, which contributed to its striking blue hue. Yet, beyond these fundamental facts, Neptune remained a profound enigma cloaked in darkness. This enigma would persist for 143 years, until a single spacecraft, operating at the very edge of its capabilities, provided humanity with its first and only close-up view of the eighth planet. What it unveiled was nothing short of astonishing. On August 25, 1989, NASA's Voyager 2 spacecraft completed the final leg of its grand tour, a rare alignment of the outer planets that allowed a single probe to visit Jupiter, Saturn, Uranus, and Neptune in succession. Voyager 2 had been journeying for 12 years, more than 4 billion kilometers from Earth. The signals from its instruments, traveling at the speed of light, took over 4 hours to reach the antennas of the Deep Space Network. Yet, in a remarkable feat of engineering that continues to inspire awe, the spacecraft arrived at Neptune just seconds from its predicted time, passing a mere 4,950 kilometers above the planet's north pole, closer than it had come to any other planet on its voyage. What Voyager 2 discovered at Neptune shattered nearly every expectation. The approach phase alone was dramatic. For weeks leading up to the closest approach, Voyager 2's cameras captured Neptune, transforming from a faint blue dot into a swirling, cloud-streaked world. Team members at the Jet Propulsion Laboratory gathered around monitors, eagerly watching each new image as it arrived. 4 hours after it was taken, racing across the solar system at the speed of light. There was no internet back then, no instant way to share these images with the world. Instead, the Voyager team held daily press conferences, revealing Neptune to the public, one photograph at a time. What those photographs revealed was nothing short of a revelation. Astronomers had presumed that Neptune, being so far from the Sun and receiving minimal solar energy, would be a tranquil, featureless world, much like Uranus, which Voyager 2 had visited 3 years earlier. Uranus, despite being closer to the Sun and slightly larger, had appeared bland and almost devoid of texture during Voyager's flyby. Its atmosphere was a hazy, uniform blue-green with few discernible features. If Uranus was that dull, then Neptune, colder, more distant, and more deprived of sunlight, should have been even less exciting. Instead, Neptune was teeming with life. The first surprise was the Great Dark Spot, a massive, dark, oval-shaped storm in Neptune's southern hemisphere, roughly the size of Earth. It bore a superficial resemblance to Jupiter's Great Red Spot, and for a time, scientists speculated whether it might be a similarly enduring feature. Around the edges of the Great Dark Spot, Voyager 2 recorded winds of astonishing velocity, reaching up to 2,100 kilometers per hour, the fastest winds ever documented on any planet. On Earth, the most powerful hurricanes generate winds of about 300 kilometers per hour. Neptune's winds were 7 times faster. They were, in essence, supersonic by terrestrial standards, though in Neptune's denser atmosphere, they remained just below the local speed of sound. A second, smaller storm, affectionately dubbed Dark Spot 2, or the Wizard's Eye, swirled at a higher latitude in the southern hemisphere. Bright, white clouds of methane ice crystals streaked across the planet's atmosphere at high altitudes, resembling cirrus clouds on Earth, though composed of frozen methane instead of frozen water. A small, fast-moving bright cloud, known as Scooter, zipped around the planet at a different speed than the surrounding storms, enhancing the sense of dynamic and complex weather patterns. But here lies the real enigma. On Earth, weather is primarily driven by solar energy. The Sun heats the atmosphere unevenly, creating temperature gradients that fuel winds, storms, and circulation patterns. Jupiter benefits from both solar heating and a vast reservoir of internal heat that stirs its atmospheric turbulence. However, Neptune receives only about 1/900th of the solar energy that Earth does. By any reasonable expectation, there simply isn't enough energy reaching Neptune from the Sun to sustain weather systems of this scale. Yet, astonishingly, Neptune radiates approximately 2.6 times more energy than it receives from the Sun. Something within the planet is generating heat, an impressive amount of it. While Jupiter and Saturn also emit more heat than they absorb, Neptune's ratio is the highest among all known giant planets in our solar system. In stark contrast, Uranus radiates almost nothing, just about 1.1 times what it receives. This presents one of the most profound puzzles in planetary science. Two planets of similar size, composition, and distance from the Sun, yet one radiates internal heat while the other remains nearly dormant. The source of Neptune's internal heat is still uncertain. One possibility is that it is residual heat from the planet's formation, the gravitational energy released as material coalesced 4.5 billion years ago, still gradually seeping out. Another theory involves ongoing gravitational settling, heavier elements slowly sinking toward the core, releasing potential energy as they descend. A third hypothesis suggests that the very process of methane transforming into diamonds contributes to this heat. As diamonds form and cascade downward through the mantle, the gravitational energy of their descent is converted into heat. Each falling diamond acts as a tiny furnace, its weight contributing infinitesimally to the planet's thermal budget. However, if leftover formation heat were the sole explanation, then Uranus, formed under broadly similar conditions, should also be radiating significant heat. The fact that it does not implies that something unique occurred with one of these planets. Perhaps Uranus suffered a catastrophic impact early in its history that caused it to lose its internal heat more rapidly. Alternatively, the internal structures of the two planets may differ in ways we have yet to comprehend. The answer remains elusive. Without a dedicated orbiter mission to either world, it may stay a mystery for decades. What is evident is that Neptune's internal heat is the driving force behind its extraordinary winds. The heat rising from its interior generates powerful convection currents that churn the atmosphere, giving rise to the massive storms and jet streams observed by Voyager 2. In a sense, Neptune's weather does not originate from above, not from the Sun, but from below, from the deep, hot interior of the planet itself. It is a world where storms are born in the shadows, and the storms themselves are far from eternal. When the Hubble Space Telescope turned its gaze toward Neptune in 1994, just 5 years after Voyager 2's historic flyby, both the Great Dark Spot and Dark Spot 2 had vanished without a trace. They were simply gone. Unlike Jupiter's Great Red Spot, which has endured for centuries, Neptune's storms emerge and dissipate within mere years. Since then, Hubble has witnessed the formation of several new dark spots in Neptune's atmosphere, each one drifting, morphing, and ultimately fading away. In 2018, a new dark spot was identified in Neptune's northern hemisphere, the first that Hubble could document from its inception. Spanning approximately 4,600 miles across, it was larger than the Atlantic Ocean. By 2020, it had unexpectedly reversed its southward trajectory, beginning to move back north, a behavior never before observed and one that no existing model had predicted. Neptune's atmosphere is a realm of relentless transformation, driven by forces we can scarcely quantify and governed by dynamics that remain elusive to us. In 2023, astronomers utilizing the European Southern Observatory's Very Large Telescope in Chile achieved a groundbreaking milestone. They observed a dark spot on Neptune from the ground for the very first time. Employing a powerful instrument known as MUSE, they analyzed the storm spectroscopically, measuring light across over 3,500 different wavelengths simultaneously. The data unveiled that these dark spots are not mere voids in the cloud cover, as some models had proposed. Instead, they seem to be regions where particles in a layer beneath the primary haze have darkened, likely due to a mixing of ices and hazes within Neptune's atmosphere. The team also discovered a novel type of bright cloud adjacent to the dark spot, at the same altitude, a deep, bright cloud that had never been identified before, not even by spacecraft. Each observation contributes a vital piece to the grand puzzle. Yet this puzzle is immense, and we are piecing it together from a staggering distance of 4.5 billion kilometers, utilizing instruments that were never intended for such a task. It is a world that challenges the notion that distance from the Sun equates to stillness. The farther we gaze, the more dynamic it becomes, and the atmosphere is merely the beginning. Beneath it lies something far more enigmatic. If you could somehow descend through Neptune's atmosphere, sinking past the methane clouds, through the layers of hydrogen and helium, deeper into the crushing pressure, you would not encounter a solid surface. There is no firm ground on Neptune, no clear boundary between atmosphere and planet. Instead, the gas gradually becomes denser and hotter, transitioning into a supercritical fluid, a state of matter that is neither gas nor liquid, but something in between. The temperature escalates, the pressure intensifies, and the composition transforms. Beneath the outer atmosphere lies what scientists refer to as the mantle, a vast expanse, thousands of kilometers thick, primarily composed of water, ammonia, and methane under extreme compression. This is not ice in any conventional sense. At the temperatures and pressures found within Neptune, reaching thousands of degrees and millions of atmospheres, these molecules behave in astonishing ways that have no counterpart on Earth. Consider water. On the surface of Earth, it freezes into solid ice at 0 degrees Celsius and boils into vapor at 100. However, in the extreme pressures found deep within Neptune, hundreds of thousands of times greater than the atmospheric pressure at sea level, water enters a remarkable phase known as super-ionic ice. In this state, oxygen atoms form a rigid crystal lattice, while hydrogen atoms dissociate from their molecules and flow freely through the structure, behaving like a liquid even as the oxygen remains solid. Super-ionic water is capable of conducting electricity and is often referred to as hot black ice, a phase of matter that exists only under such extreme conditions that they were once thought to be purely theoretical until scientists managed to recreate them in laboratories with powerful lasers. In 2018, researchers at Lawrence Livermore National Laboratory compressed water to pressures exceeding 1 million atmospheres and heated it to thousands of degrees, directly observing the formation of super-ionic ice for the first time. This material was both crystalline and electrically conductive, ice that was simultaneously solid and liquid depending on which atoms you examined. It existed for only a fleeting moment before the experimental conditions collapsed. But in that brief instant, scientists confirmed the existence of a phase of matter that had been predicted by theory decades earlier. Within Neptune, these conditions are not transient, they are permanent. Deep in the planet's mantle, a vast layer of super-ionic water may persist continuously, with its oxygen lattice remaining rigid while hydrogen ions flow like a fluid current. It is this current, this movement of charged particles through a crystalline matrix, that may generate Neptune's magnetic field. Most planets with magnetic fields produce them through a dynamo process, the swirling of electrically conductive material within the planet's interior, driven by convection and rotation. On Earth, this dynamo operates in the liquid iron outer core. On Jupiter and Saturn, it functions within a deep layer of metallic hydrogen. Yet Neptune's magnetic field behaves differently from all of these. Voyager 2 measured Neptune's magnetic field and discovered it to be profoundly asymmetric. The magnetic axis is tilted 47 degrees from the planet's rotational axis, far more than Earth's modest 11-degree tilt. Even more striking, the center of the magnetic field is offset from the planet's geometric center by approximately 0.55 Neptune radii, over 13,500 kilometers. This indicates that the magnetic field is not generated at the planet's core. Rather, it originates somewhere in the outer layers of the interior, possibly within the thin shell of electrically conducting fluid, perhaps the superionic water layer or the ionic ocean above it. Before Voyager 2 reached Neptune, scientists had assumed that Uranus's wildly tilted magnetic field, 59 degrees from its rotation axis, was a result of its extreme axial tilt. After all, Uranus rotates on its side. However, Neptune's axis is tilted only 28 degrees from vertical, much like Earth's. Yet its magnetic field is nearly as distorted as that of Uranus. The two ice giants exhibit this peculiar magnetic geometry despite their differing orientations. This suggests that the unusual magnetic fields of ice giants are not merely a consequence of their tilts. Instead, they stem from the internal structure of the ice giant planets themselves, from the thin, shallow shell of conducting fluid in which the dynamo operates. This is not just an intriguing curiosity. It has significant implications for our understanding of thousands of exoplanets. Ice giants in the mass range of Uranus and Neptune are among the most common types of planets discovered orbiting other stars. If we misinterpret how magnetic fields are generated in these worlds, we risk misunderstanding a fundamental process that operates throughout the galaxy. Deep within the enigmatic depths of Neptune, an extraordinary process unfolds, one that seems to leap straight from the pages of science fiction, yet finds its roots in laboratory experiments. At a staggering depth of approximately 7,000 kilometers beneath Neptune's swirling cloud tops, where pressures soar to hundreds of thousands of atmospheres and temperatures spike into the thousands of degrees, methane molecules, composed of one carbon atom bonded to 4 hydrogen atoms, may undergo a dramatic transformation. The hydrogen is stripped away, and the liberated carbon atoms, subjected to immense pressure, are compelled into a compact tetrahedral lattice structure, forming diamond. Picture this: diamond rain cascading through Neptune's mantle, plunging through layers of superheated, supercritical fluid, slowly making its way toward the core. In 2017, scientists at the SLAC National Accelerator Laboratory harnessed high-powered lasers to replicate the extreme conditions found within ice giant planets, directly observing the formation of tiny nanodiamonds from carbon-rich materials under intense pressure. By 2022, further experiments utilizing a substance that closely mimics Neptune's internal composition, not just carbon and hydrogen, but also oxygen, revealed that diamonds formed even more readily than anticipated. The presence of oxygen accelerated the process, suggesting that diamond rain could occur at shallower depths and under a broader range of conditions than previously thought. If this phenomenon is indeed real, and the laboratory evidence is compelling, then deep within Neptune, diamonds the size of pebbles, or perhaps even larger, may be perpetually falling through the mantle. Some researchers speculate that these diamonds could grow to weigh millions of carats, single crystals of carbon surpassing any gem ever found on Earth. Over billions of years, these diamonds may accumulate around the planet's core, creating a thick, glittering shell of carbon crystal encasing the rocky heart of Neptune. Imagine it, a layer of diamond, hundreds or even thousands of kilometers thick, entombing the core of a world forever hidden from human eyes. The energy released as these diamonds sink through the mantle, the gravitational energy of their descent, would contribute to Neptune's internal heat budget, helping to explain why the planet radiates significantly more energy than it receives. On Earth, diamonds symbolize wealth, permanence, and desire. Entire economies revolve around their extraction and trade, and wars have been fought over them. Yet on Neptune, they are merely a byproduct of physics, common, natural, and eternal. The universe does not bestow value upon them, it produces them as effortlessly as a river produces sand. In tandem with the diamonds, experiments have also detected the formation of superionic water, the same exotic phase of matter that may generate Neptune's magnetic field. These two processes are intertwined, diamond rain and superionic ice falling and forming together in the crushing darkness of Neptune's interior, fueling the planet's heat, shaping its magnetic field, and driving its supersonic winds. This is not the Neptune depicted in textbook diagrams, a smooth blue circle adorned with a few labeled features. This is a realm of extraordinary internal complexity, where carbon crystallizes into gems and water transforms into a conductor of electricity, where the boundaries between solid, liquid, and gas dissolve under pressures that no earthly material could endure. At the heart of it all, the exotic chemistry, the peculiar magnetic field, the internal heat, lies a singular truth. Neptune is an ice giant. Unlike gas giants such as Jupiter or Saturn, which are primarily composed of hydrogen and helium, Neptune represents a fundamentally different type of planet, constructed from heavier materials, water, ammonia, methane, that existed as solid ices in the frigid outer reaches of the solar nebula during its formation. These ices constitute roughly 80% of Neptune's mass, providing the planet with its density, chemistry, and undeniable strangeness. But Neptune didn't always reside where it is today. To grasp the reasons behind this, we must journey back to the tumultuous early days of our solar system, a chaotic 100 million years that witnessed a migration so intense it transformed everything we know. 4.5 billion years ago, the solar system was far from the orderly arrangement of planets we recognize now. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, were tightly packed in a much more compact formation, all orbiting within a mere 15 to 20 astronomical units from the Sun. At that time, Neptune, the most distant of the four, might have been closer to the Sun than Uranus, and it's possible that these two ice giants completely swapped their positions during their formative years. Beyond the orbits of these giant planets lay a colossal disk of icy planetesimals, small frozen remnants from the solar system's formation. This disk, stretching from just beyond the outermost giant planet to perhaps 30 or 35 astronomical units, contained an estimated 30 to 50 Earth masses worth of material. It was dense, frigid, and brimming with potential energy. This very disk would eventually set the outer solar system into motion. The unfolding narrative of what happened next is encapsulated in a model crafted in 2005 by a team of astronomers in Nice, France, aptly named the Nice model. In this model, the giant planets initially orbited in a stable, resonant configuration, each planet locked in a gravitational dance with its neighbors, much like gears in a finely tuned clock. Jupiter and Saturn may have been in a 3-to-2 resonance, with Jupiter completing 3 orbits for every 2 of Saturn's. The ice giants were similarly intertwined, orbiting in compact, nested resonances. This arrangement remained stable for hundreds of millions of years. However, it was not destined to last. Gradually, almost imperceptibly, the outer edge of the planetesimal disk began to interact with Neptune. Individual icy bodies were nudged inward, exchanging orbital energy with the outermost giant planet. Neptune began to drift outward. The resonances between the planets started to shift. And then, somewhere between 500 million and 1 billion years after the solar system's birth, this resonant configuration unraveled. What ensued was a period of dramatic instability. Jupiter and Saturn crossed a critical resonance, likely the 2-to-1 resonance, where Jupiter completed exactly 2 orbits for every one of Saturn's. This crossing injected energy into the orbits of all 4 giant planets, disrupting their delicate arrangement. Uranus and Neptune were propelled outward into the planetesimal disk, carving through the frozen bodies like ships navigating a bustling harbor, scattering planetesimals in every direction. To truly appreciate the magnitude of this upheaval, envision the primordial planetesimal disk as a vast, frozen ocean of small, icy worlds. Tens of Earth masses of material, billions upon billions of individual objects, quietly orbiting in the outer solar system for hundreds of millions of years. And then Neptune arrives, charging through on an expanding orbit, its gravity stirring this frozen ocean into turmoil. Bodies that had orbited peacefully for eons were suddenly yanked onto new paths. Some were hurled inward toward Jupiter, which, in turn, expelled most of them from the solar system entirely. Others were launched onto elongated, inclined orbits, carrying them far above and below the plane of the solar system. A fortunate few were captured into resonant orbits that would ensure their stability for billions of years. The rest were lost to the void. The consequences were nothing short of catastrophic and reverberated throughout the cosmos. Planetesimals were hurled inward toward the inner solar system, unleashing a barrage upon the terrestrial planets and the Moon in an event that likely corresponds to the late heavy bombardment, a tumultuous period around 3.9 billion years ago when the rate of impacts on the Moon and Earth surged dramatically. Others were cast outward, far beyond the original disk, populating the scattered disk and the Oort cloud, that vast, spherical shell of icy bodies extending halfway to the nearest star. The primordial Kuiper Belt, once a dense, compact disk of icy bodies situated just beyond the giant planets, was effectively obliterated. Neptune's outward migration swept through it, capturing some objects into resonant orbits, scattering others onto chaotic trajectories, and ejecting the overwhelming majority from the solar system altogether. Current estimates suggest that over 99% of the original mass of the primordial Kuiper Belt was lost in this tumultuous process. What remains today, the thin, depleted belt of icy objects we observe between approximately 30 and 50 astronomical units, is but a shadow of its former self, a remnant, a ruin. And it was Neptune that wielded the instrument of this ruin. As it migrated outward, its mean motion resonances, the orbital ratios where Neptune's gravity exerts its most potent influence, swept through the disk like invisible nets, ensnaring some objects while obliterating others. Take Pluto, for example, which is ensnared in a 3-to-2 resonance with Neptune. For every 3 orbits Neptune completes, Pluto completes 2. This is no mere coincidence. Pluto was captured into this resonance during Neptune's migration and has remained there ever since. Hundreds of other trans-Neptunian objects share this resonance. They are known as Plutinos, and their existence stands as one of the strongest pieces of evidence for Neptune's migration. The NICE model, in its various iterations, has proven remarkably adept at elucidating the large-scale architecture of the outer solar system. It accounts for the resonant populations within the Kuiper Belt. It explains the scattered disk. It even provides a mechanism for the late heavy bombardment. It even clarifies why Jupiter possesses Trojan asteroids, small bodies that share its orbit, with characteristics suggesting they were captured from the outer solar system during this migration. Yet, certain details remain shrouded in uncertainty. The precise timing of the instability is still a matter of debate. Some versions of the model posit the existence of a 5th giant planet, an additional ice giant that was expelled from the solar system entirely during the instability, flung into interstellar space by Jupiter's gravity, never to return. The 5-planet NICE model is now deemed more consistent with the observed structure of the Kuiper Belt than its original 4-planet counterpart. Consider that for a moment. Our solar system may have once harbored 5 giant planets. One of them may have been lost, cast into the void between the stars during the same upheaval that propelled Neptune to its current orbit. Imagine a planet the size of Neptune or Uranus wandering through interstellar space for 4 billion years, invisible and alone, its surface frozen by the chill of the void. its atmosphere slowly condensing and collapsing as it drifted farther and farther from any star. We would remain oblivious to its existence were it not for the scars of its ejection etched in the distribution of icy bodies at the solar system's edge. The inclination distribution of the hot classical Kuiper Belt, the spread of orbital tilts among its members, is more accurately reproduced by models that incorporate a fifth planet. The orbital eccentricities of certain scattered disk objects become more comprehensible if an additional ice giant was present during the instability. The evidence may be indirect, but it is mounting, and the implications are profound. The solar system we inhabit may not be the solar system that was originally formed. A piece of it is missing. The Kuiper Belt is far more than just a collection of icy remnants. It is a cosmic crime scene, with Neptune playing the dual role of both detective and suspect. What makes Neptune's current location so astonishing is that it is not its birthplace, but rather the result of a tumultuous journey that reshaped the outer solar system's original design. Every characteristic of the Kuiper Belt, from the resonant populations to the scattered disk, the cold classical belt, and the peculiar detached objects with their distant orbits, bears the unmistakable mark of Neptune's influence. The planet that seems out of place is, in fact, the very force that orchestrated the arrangement of everything else. Neptune's impact on the outer solar system is ongoing. Its gravitational pull is not merely a remnant of history, it is a dynamic force that continues to mold the celestial landscape. The mean motion resonances it generates persist in capturing and sculpting the orbits of Kuiper Belt objects. Its gravitational nudges sustain the scattered disk, propelling icy bodies onto paths that draw them closer to the Sun, where some eventually transform into short-period comets. Each comet that streaks across our night sky with a cycle of less than about 200 years, every one of those ethereal visitors trailing a shimmering tail of gas and dust, was almost certainly ushered into the inner solar system by Neptune's gravitational sway, either directly or through the scattered disk it created. The comets that humanity has gazed upon with awe and trepidation throughout history, objects of folklore, subjects of verse, catalysts for scientific breakthroughs, are, in a profound way, messengers of Neptune. They are remnants of the frozen disk that Neptune disrupted 4 billion years ago, still making their way inward one by one as Neptune's distant gravity continues to agitate the far reaches of the solar system. Even at a distance of 30 astronomical units, Neptune's influence stretches far beyond its immediate vicinity. It stands as the gatekeeper of the outer solar system. Neptune did not merely scatter the primordial Kuiper Belt during its migration. It also claimed something remarkable. What it took is one of the most extraordinary objects in our solar system. Triton, Neptune's largest moon, is a captive celestial body. With a diameter of 2,710 kilometers, Triton ranks as the seventh largest moon in the solar system, slightly larger than the dwarf planet Pluto, and shares a nearly identical composition. Its density, surface ices, and thin nitrogen atmosphere all indicate that Triton and Pluto originated from the same region of the outer solar system. In a sense, they are cosmic siblings. Yet, Triton is not in its rightful place. It orbits Neptune in a retrograde direction, opposite to the planet's spin. This is remarkably unusual. All large moons that formed alongside their parent planets typically orbit in the same direction as the planet's rotation, having coalesced from the same disk of material that birthed the planet itself. A retrograde orbit for a large moon is a hallmark of capture. Triton did not form in Neptune's vicinity, it was taken from elsewhere. The most widely accepted theory involves a binary exchange. In the early solar system, many Kuiper Belt objects existed as binary pairs, two bodies orbiting one another as they journeyed around the Sun. If such a binary system ventured too close to Neptune, the gravitational interaction could tear the pair apart, capturing one member in orbit around Neptune while casting the other into the vastness of interstellar space. Computer simulations suggest that this process is not only plausible, but may have been relatively common during Neptune's outward migration, a time when the planet encountered a multitude of Kuiper Belt objects. The capture of Triton was anything but gentle. Once ensnared, Triton would have embarked on a highly elliptical, eccentric orbit around Neptune. Each time it swung close to the planet, tidal forces would have flexed its interior, generating immense heat. As it retreated, that heat would have partially dissipated. This relentless cycle, approach, flex, heat, retreat, cool, and then approach again, would have persisted for millions of years, gradually shrinking and circularizing its orbit while heating Triton to the brink of partial or complete melting. Now, envision this from Neptune's perspective, though, of course, there was no one there to witness it. A body the size of a small planet, larger than Pluto, suddenly appeared in orbit. Not in a tidy circular path, but in a wild, looping trajectory that brought it screaming close to Neptune before flinging it back out to vast distances. Each close pass would have disrupted the orbits of every other moon in the system, creating gravitational earthquakes felt by every body in orbit around Neptune. The tidal forces between Triton and Neptune, the stretching and compressing of rock and ice driven by gravity, would have been monumental. These tides dissipated energy, gradually circularizing Triton's orbit over millions of years. Today, Triton's orbit is nearly perfectly circular, with an eccentricity of just 0.00001, a testament to the billions of years of tidal interactions that have unfolded since its capture. However, this circularization came at a significant cost. As Triton's orbit shrank and became more circular, the tidal forces generated tremendous heat within the Moon. Triton may have been partially or entirely molten during this transformation. Its interior melted, its surface reshaped, and any original satellite system that Neptune possessed, moons that had formed alongside the planet in a more conventional manner, would have been obliterated. Triton's arrival was catastrophic for Neptune's original moons. Computer simulations indicate that the gravitational disruption caused by a massive body on a wild, inclined retrograde orbit would have destabilized the orbits of any existing regular satellites, leading to collisions or ejections from the system entirely. This phenomenon explains a curious aspect of Neptune's current moon system. Apart from Triton, Neptune is home to only small, irregular moons, lacking the large, orderly satellites that define the systems of Jupiter, Saturn, and Uranus. Neptune's moon system appears fragmented. Triton is the reason behind this. The captured world annihilated what existed before it and now dominates the system, containing over 99.5% of all the mass orbiting Neptune. And Triton's story is far from over. Due to its retrograde orbit, tidal interactions between Triton and Neptune are gradually siphoning energy from the Moon's orbit. Triton is spiraling inward. In approximately 3.6 billion years, it will cross Neptune's Roche limit, the distance at which tidal forces will tear it apart. When that moment arrives, Triton will be shredded into fragments, potentially forming a ring system around Neptune that could rival Saturn's. The planet that stole a world from the Kuiper Belt will ultimately be its destroyer. For now, however, Triton remains a world of extraordinary intrigue. Voyager 2 flew past it during its 1989 encounter with Neptune, revealing a surface that is astonishingly young, less than 100 million years old and possibly even younger than 10 million years. The near absence of impact craters suggests that something is perpetually reshaping Triton's surface. Voyager 2 captured images of active geysers, plumes of nitrogen gas erupting from the surface to heights of about 8 kilometers, only to be swept sideways by thin atmospheric winds, leaving dark streaks on the icy terrain. These geysers may be driven by a solid-state greenhouse effect, where sunlight penetrates the transparent nitrogen ice, heats a darker layer beneath, and vaporizes the nitrogen from below. Triton's surface presents a surreal tableau of frozen plains, intricate fractures, and a region of undulating terrain, affectionately dubbed the cantaloupe terrain, due to its striking resemblance to the textured skin of a melon. The origins of this peculiar landscape remain shrouded in mystery. It could be the result of diaporism, where warmer, less dense materials rise through the crust like blobs in a lava lamp, giving rise to its rounded, dimpled appearance. Alternatively, it may stem from convection processes within a near-surface layer of ice. Regardless of its formation, this terrain stands alone in the solar system, with no exact counterpart elsewhere. The polar caps, composed of nitrogen and methane ice, shine with an albedo so high that Triton reflects approximately 70% of the sunlight that reaches it, a brightness surpassing that of fresh snow on Earth. With surface temperatures hovering around -235 degrees Celsius, Triton ranks among the coldest surfaces measured in our solar system, with only Pluto occasionally rivaling it in some assessments. Imagine standing on Triton's surface, clad in an extraordinary spacesuit, braving the frigid conditions that would render any known material solid, and you would behold a landscape of pinkish-white ice stretching toward a gently curving horizon. The sky above would be a deep black, punctuated by countless stars. Neptune would loom large in this celestial expanse, appearing as a vast blue crescent, many times larger than the full moon as seen from Earth, its swirling bands and storms discernible even to the naked eye. The sun would be a brilliant point of light, casting shadows that, while dim, would be sharply defined. Beneath your feet, tens of kilometers of solid ice would lie between you and a hidden ocean that might, against all odds, possess the conditions necessary for life. Beneath that icy crust, there may exist liquid water. Triton is a differentiated body. Its interior comprises a rocky core, an icy mantle, and a frozen crust. The tidal heating resulting from the circularization of its orbit, combined with potential residual radiogenic heating from its rocky core, may have fostered and sustained a global subsurface ocean. Models indicate that this ocean could still be present today, insulated beneath a thick shell of ice, possibly enriched with ammonia, a factor that would lower its freezing point and allow liquid water to persist even under Triton's frigid conditions. A captured Kuiper Belt dwarf planet exhibiting active geology, nitrogen geysers, a youthful surface, and a potential ocean beneath its icy veneer, Triton emerges as one of the most intriguing astrobiological targets in the outer solar system, second only to Europa and Enceladus. Its existence is a testament to the fact that Neptune stole it away. The timing of Triton's capture, whether it occurred during Neptune's outward migration or at another point in time, remains an open question. A 2024 study comparing the chemical compositions of Pluto and Triton revealed that both worlds share similar nitrogen abundances, along with trace amounts of methane and carbon monoxide, suggesting they formed in the same region of the outer solar nebula. These two worlds began their journey in the same cosmic cradle. One remained free, while the other was claimed. Neptune's atmospheric differential rotation is the most extreme of any planet in the solar system. Near the equator, the atmosphere rotates with a period of about 18 hours, significantly slower than the planet's internal rotation period of 16.1 hours, as determined by the rotation of its magnetic field. At higher latitudes, particularly near the poles, the atmospheric rotation accelerates, achieving periods as brief as 12 hours. This phenomenon reveals that Neptune's equatorial atmosphere moves in reverse relative to the planet's interior, a striking occurrence known as superrotation in the opposite direction, or more specifically, retrograde equatorial winds. Near the equator, Neptune's winds whip westward at astonishing speeds, nearing 2,100 kilometers per hour when measured against the planet's interior. As we move to higher latitudes, the winds shift to an eastward direction, reaching speeds of about 900 kilometers per hour. This creates a colossal shear between various latitude bands, a vast system of jet streams and counterstreams that gives rise to the turbulent, ever-shifting weather patterns captured by Voyager 2 and the Hubble Space Telescope. The physics behind these winds remains somewhat elusive. One theory, put forth shortly after Voyager 2's historic flyby, posits that Neptune's winds are fueled by deep convection, where heat from the planet's interior generates large-scale circulation cells that transport angular momentum toward the equator, resulting in the observed retrograde equatorial winds and prograde polar winds. In this scenario, the winds are not merely surface-level phenomena driven by solar heating, as we see on Earth. Instead, they are the result of profound atmospheric processes deeply rooted in the planet's internal heat. However, measurements of Neptune's gravitational field, derived from Voyager 2's trajectory as it traversed Neptune's gravitational pull, indicate that these winds are confined to an astonishingly thin layer. The windy regions of Neptune occupy merely the outermost 0.2% of the planet's total mass. This layer is approximately 1,000 kilometers deep, considerable by earthly standards, yet a minuscule fraction of Neptune's overall diameter of about 49,500 kilometers. Beneath this slender weather layer, the planet's interior rotates as a solid mass. How can such a narrow layer produce the fastest winds in the solar system? One possibility is that Neptune's atmosphere, despite receiving minimal solar energy, is remarkably adept at converting internal heat into kinetic energy. The stark temperature contrast between the scorching interior and the icy cloud tops creates a heat engine with exceptional efficiency. The frigid temperatures at the cloud tops, just 55 Kelvin, a mere few dozen degrees above absolute zero, mean that the upper atmosphere serves as an excellent cold reservoir, enabling the heat engine to extract maximum work from the temperature differential. In thermodynamic terms, Neptune's atmosphere operates near the Carnot limit, the theoretical pinnacle of efficiency for a heat engine. This finding is both extraordinary and counterintuitive. A planet that basks in almost no sunlight, shrouded in perpetual twilight, harbors an atmospheric heat engine of remarkable efficiency, precisely because of its extreme cold. This coldness is not a barrier, it is the driving force. The very darkness that renders Neptune seemingly lifeless is what fuels its atmosphere's violent activity. Now let's draw a comparison with Earth. Our planet's atmosphere functions at a relatively warm average temperature, with modest temperature gradients between the equator and the poles. By thermodynamic standards, the efficiency of Earth's atmospheric heat engine is quite low. Much of the solar energy that enters our atmosphere is re-radiated as waste heat, without ever generating wind or weather. In stark contrast, Neptune's atmosphere exists at temperatures close to absolute zero at its upper boundary, while its interior may soar to thousands of degrees. This immense temperature gradient creates the ideal conditions for an extraordinarily efficient conversion of thermal energy into motion. Less energy is required, yet the extraction is far more effective. The outcome is winds that dwarf anything found on Earth, Jupiter, or Saturn. The implications of this discovery extend far beyond the icy realm of Neptune. If the atmospheres of ice giants are inherently more adept at transforming internal heat into dynamic atmospheric circulation, then the myriad mini-Neptunes and ice giant exoplanets orbiting distant stars could very well host similarly tumultuous weather patterns. A category of planets we once considered to be cold and tranquil may, in reality, represent the most tempestuous class of worlds in the galaxy. Imagine for a moment descending through Neptune's atmosphere. A thought experiment, as no spacecraft has ever embarked on such a journey. the experience would be unlike anything found on Earth. You would begin in near total darkness, with the Sun over 4 billion kilometers away, appearing as a distant star, perhaps 64 times dimmer than its midday brilliance on our planet. The temperature would plummet to around -220 degrees Celsius, while winds would whip past you at supersonic speeds. As you continued your descent, the atmosphere would thicken and the deep blue hue would intensify. Methane clouds would yield to layers of hydrogen sulfide and ammonium hydrosulfide. The pressure would escalate, 2 bars, 5 bars, 10 bars, and the temperature would begin to rise as the internal heat made its presence known. The line between gas and liquid would blur, and at some point, the atmosphere would become so dense that it would feel more like an ocean than a sky. You would find yourself suspended in a superheated, supercritical fluid, enveloped by crushing pressure, with no solid ground beneath you and no sky above, only an ever-deepening darkness. And far below, in the unimaginable pressures of Neptune's deep mantle, carbon atoms would crystallize into diamonds, silently drifting through the fluid, sparkling in a darkness untouched by any light. Neptune's ring system is faint, shadowy, and incomplete. In stark contrast to the magnificent rings of Saturn, which are bright, expansive, and visible even through modest telescopes, Neptune's rings are narrow, composed of dark material, and so tenuous that their existence was only confirmed when Voyager 2 arrived in 1989. Ground-based observations in the 1980s had detected brief dimming events as stars passed behind Neptune, indicative of ring arcs but not complete rings. The prevailing theory suggested that Neptune possessed a system of incomplete arcs rather than full rings, a conundrum in itself, as gravitational dynamics should cause arcs to spread into complete rings over relatively short timescales. Voyager 2 unveiled the reality. Neptune boasts 5 principal rings, named Adams, Leverrier, Lassell, Arago, and Gall, in honor of the astronomers associated with Neptune's discovery and early study. The outermost ring, Adams, stands out as the most distinctive. It contains 5 bright, dense arcs, named Courage, Liberté, Égalité 1, Égalité 2, and Fraternité, that are concentrated within a small segment of the ring's circumference. The remainder of the Adams ring is considerably fainter. The confinement of these arcs is thought to be sustained by the gravitational influence of Galatea, a small moon orbiting just within the Adams ring. Galatea's gravity creates resonances that prevent the arc material from dispersing. However, these arcs are not stable over the long term. Observations from the Hubble Space Telescope and ground-based telescopes have revealed that the arcs are evolving. Some have faded, and the distribution of material within them has shifted over the decades since Voyager 2's visit. Neptune's rings may be transient features, continually replenished by material from micrometeorite impacts on the small inner moons, while gradually dispersing under the influence of solar radiation and gravitational perturbations. The rings of Neptune are a fascinating spectacle, primarily composed of ice particles and silicate dust, much of which has been darkened through radiation processes. This darker hue sets them apart from the bright, icy rings of Saturn and contributes to their near invisibility from our vantage point on Earth. Neptune's ring system is fragile, dynamic, and remains shrouded in mystery. Yet another intriguing aspect of this distant planet that continues to elude our full understanding. Let's take a moment to appreciate a striking visual detail. Neptune's color, a rich, vibrant blue, has recently been the subject of fresh scrutiny. For decades, the images that linger in the public consciousness were captured by Voyager 2, showcasing Neptune in a stunningly deep azure, far bluer than Uranus. These iconic images adorned textbook covers and posters, solidifying Neptune's reputation as the blue planet of the outer solar system. However, in 2024, researchers revisited the original Voyager 2 data using advanced techniques, revealing that the perceived difference between Neptune and Uranus had been exaggerated. The original Voyager team had enhanced Neptune's contrast to highlight atmospheric features that would otherwise remain hidden. A scientifically sound choice, yet one that inadvertently rendered Neptune's color overly vivid and intensely blue. In truth, Neptune and Uranus share a much closer resemblance in appearance than most people realize, with both planets exhibiting a pale blue-green hue, Neptune being only slightly deeper in tone. The blue coloration arises from methane present in the upper atmosphere, which absorbs red wavelengths of sunlight while reflecting blue. However, the precise shade and the reason Neptune appears slightly bluer than Uranus, despite their similar compositions, may hinge on the thickness and characteristics of the haze layers in each planet's atmosphere. A thinner haze on Neptune would permit more of the methane's absorption to be visible, resulting in a deeper blue. Grasping this seemingly minor detail about color necessitates a comprehensive understanding of Neptune's atmospheric vertical structure, insight that a flyby mission cannot provide, but which an orbiter could elucidate in full. Speaking of reach, Neptune boasts 16 known moons as of the latest surveys, a number that continues to rise as telescopic technology advances. Most of these moons are small, irregularly shaped, and likely captured objects. Only Triton is substantial enough to be shaped by its own gravity. The next largest moon, Proteus, is irregular and heavily cratered, measuring about 420 kilometers across. Another noteworthy moon, Nereid, possesses one of the most eccentric orbits of any moon in the solar system, with its distance from Neptune varying by nearly a factor of 7 between its closest and farthest points. This extreme eccentricity may be a direct result of Triton's capture, which could have gravitationally perturbed Nereid into its current erratic orbit. Neptune's moon system serves as a testament to the aftermath of cosmic events. Triton reigns supreme, having obliterated whatever existed before. The smaller survivors, Proteus, Nereid, Larissa, Galatea, Despina, and others, are either remnants of the original system or objects that were captured later on. Unlike the orderly, graduated structures found around Jupiter, Saturn, or Uranus, Neptune's system is shaped by chaos and chance. To comprehend how Neptune arrived at its current state, we must journey back to the early solar system, specifically the first few million years when the Sun was a nascent star enveloped by a swirling disk of gas and dust. Within this primordial disk, gravity began to coalesce material. Close to the Sun, where temperatures soared, only rocky and metallic substances could condense, giving rise to the terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, beyond a threshold known as the snow line, temperatures were low enough for water, ammonia, and methane to solidify into ices. These ices provided essential building blocks, enabling protoplanets to grow larger and more rapidly. Jupiter was the first to take shape, forming in the inner solar system, where the protoplanetary disk was still rich with materials. Its core, composed of approximately 10 to 15 Earth masses of rock and ice, grew rapidly, allowing it to start capturing hydrogen and helium gas before the solar wind could disperse the remaining gas. This led to Jupiter's colossal size, a staggering 318 Earth masses, a massive sphere of compressed hydrogen and helium enveloping a dense core. Following closely behind, Saturn emerged through a similar process, reaching about 95 Earth masses. Both giants crossed a pivotal threshold. Once a core accumulates enough mass, around 10 Earth masses, it begins to gravitationally attract gas from the surrounding nebula at an accelerating pace, a phenomenon known as runaway gas accretion. This is the hallmark of a gas giant. It's not just about size, but about achieving critical mass while gas is still plentiful. In contrast, the ice giants, Uranus and Neptune, were not as fortunate. Forming at a greater distance from the Sun, they encountered a thinner disk where accretion was sluggish. Time was against them. T-Tauri stellar winds from the nascent Sun were already stripping gas from the outer nebula. By the time their rocky, icy cores reached several Earth masses, the gas disk was dissipating. They managed to capture some hydrogen and helium, but significantly less than their gas giant counterparts. This is why they are classified as ice giants rather than gas giants. Their composition is primarily heavy elements, with only a thin layer of hydrogen and helium making up about 20% of their mass. They represent the solar system's almosts, the planets that nearly became gas giants but missed their opportunity. However, the conventional model of in situ formation encounters a significant challenge. At Neptune's current distance of 30 astronomical units from the Sun, the solar nebula was so sparse that it would have taken far longer than the solar system's age for a planet of Neptune's mass to form. The calculations simply don't add up. A planet cannot develop at 30 astronomical units within the lifespan of a protoplanetary disk. This is where the concept of migration becomes crucial. Neptune did not originate at 30 astronomical units. It formed much closer to the Sun, likely between 15 and 20 astronomical units, possibly even nearer. Models indicate that Neptune may have initially orbited within the present orbit of Uranus. The two ice giants might have formed in the reverse order of their current positions, with Neptune originally being the inner planet. The outward migration, propelled by gravitational interactions with the planetesimal disk, carried Neptune from about 20 astronomical units to its current location at 30 astronomical units, a staggering journey of roughly 10 astronomical units, or about 1.5 billion kilometers. This is an extraordinary distance for a planet to traverse. Moreover, the migration was anything but smooth. The NICE model, especially in its more recent 5-planet iterations, describes a phase of chaotic instability during which the giant planets experienced close gravitational encounters, exchanged energy, and dramatically altered their orbits. Amid this turmoil, Neptune was flung outward into the planetesimal disk, where it began its slow, grinding migration to 30 astronomical units. As it journeyed, its mean motion resonances swept through the disk like invisible brooms, capturing some objects, destabilizing others, and ejecting the vast majority. The structure of today's Kuiper Belt, its resonant populations, its cold and hot classical components, its scattered disk, serves as a direct testament to this migration. The gravitational imprint of Neptune's journey resonates throughout the outer solar system. Consider Pluto, locked in its 3:2 resonance, alongside the Plutinos and the Teutinos, which exist in their own 2:1 resonance. Then we have the cold classical belt, a collection of low-inclination objects nestled between 42 and 48 astronomical units, likely formed in situ and largely untouched by Neptune's migration. In contrast, the hot classical belt comprises higher inclination objects that were scattered into their current paths by Neptune's gravitational pull. Lastly, the scattered disk objects, with their wildly elongated orbits, swing close to Neptune at perihelion before retreating far into the solar system's outer reaches. Each of these groups contributes a unique chapter to the narrative. Together, they weave a tale of a solar system dramatically reshaped by the movement of a single planet. The cold classical belt stands out as particularly poignant. These objects, orbiting between approximately 42 and 48 astronomical units, exhibit low inclinations and eccentricities, tranquil, undisturbed paths that imply they have remained in their positions since the dawn of time. Many of them are binaries, two small icy bodies revolving around one another as they journey around the Sun, bound by the faintest gravitational ties. The endurance of these delicate binaries reveals something remarkable. Despite the upheaval caused by Neptune's migration to the majority of the primordial disk, this narrow region has somehow remained largely intact. The cold classical belt is a remnant of the original solar nebula. a strip of primordial material that withstood the passage of a migrating planet. It represents the oldest, most pristine sample of the early solar system accessible to us. In stark contrast, the hot classical belt consists of objects that were scattered into their current orbits by Neptune. These bodies display higher inclinations and a broader spectrum of eccentricities. They are the immigrants, formed closer to the Sun and ejected outward during Neptune's migration. Their appearances also differ. Their colors are more varied than the uniformly red, cold classical objects, hinting at diverse formation environments. And then we encounter the scattered disk, a collection of objects on highly elongated orbits that bring them near Neptune at perihelion before sending them hundreds of astronomical units away from the Sun. These are the objects that Neptune nudged but could not fully expel. They remain loosely tethered to the solar system, their orbits still influenced by Neptune's distant grasp, gradually evolving over billions of years. Neptune is the architect of the outer solar system. The Kuiper Belt is its magnum opus, not a primordial feature, but a sculpted, refined, and diminished remnant of something far more massive and orderly. There's a broader motivation for studying Neptune, one that transcends our own solar system. When astronomers began identifying planets around other stars in the 1990s, they anticipated discovering solar systems resembling ours, small, rocky planets close to their stars, with gas giants further out. Instead, they encountered a diverse array of planetary configurations that defied all expectations. Hot Jupiters orbiting their stars in mere days, super-Earths tightly packed together, mini-Neptunes, planets falling between Earth and Neptune in mass, emerged as the most common type of planet in the galaxy. This last observation is crucial. Our solar system lacks a planet within the super-Earth or mini-Neptune mass range. Every planet we possess is either significantly smaller than Neptune, the terrestrial planets, or considerably larger, the gas giants. However, surveys of exoplanetary systems have revealed that the most prevalent planets in the Milky Way, by a considerable margin, occupy precisely this intermediate range. They are the planets that our solar system, for reasons unknown, failed to create. Neptune and Uranus stand as the only ice giants in our solar system, serving as our closest representatives of a prevalent class of exoplanets. Delving into their interiors, atmospheres, magnetic fields, and formation histories transcends the mere cataloguing of our solar system's planets. It is essential for grasping the most common type of planet in the universe. Now, let's reflect on the vast unknowns that surround us. We remain uncertain about the precise composition of Neptune's interior. What is the ratio of rock to ice? At what depth does superionic water emerge? What is the exact pressure threshold for diamond rain to commence? Despite their nearly identical size and bulk composition, why does Neptune emit significantly more internal heat than Uranus? The intricate structure of Neptune's magnetic field eludes us. Voyager 2 captured data during a single flyby, from one angle, on one day. We lack insights into the long-term behavior of Neptune's atmospheric storms. Do they operate on a cycle? Are they becoming more or less frequent? Are wind speeds shifting over decades? We are also in the dark about whether Triton harbors a subsurface ocean. The composition of Neptune's rings remains largely a mystery, and the count of Neptune's moons, currently at 16, is almost certainly an understatement. Each of these mysteries holds implications that reach far beyond our solar neighborhood. The rock-to-ice ratio in Neptune informs models of how ice giant cores form, which in turn shapes our understanding of the formation histories of countless exoplanetary ice giants. The structure of its magnetic field reveals the depth and makeup of the dynamo region, shedding light on the internal chemistry of all ice giants. The dynamics of its atmosphere provide insights into weather patterns in hydrogen, helium, methane atmospheres, crucial for characterizing exoplanetary atmospheres through the James Webb Space Telescope and its successors. In essence, Neptune serves as a Rosetta Stone for an entire category of worlds. Yet we have barely scratched the surface. Remarkably, we know less about Neptune and Uranus than any other planet type in our solar system. We have dispatched orbiters to Mercury, Venus, Mars, Jupiter, and Saturn. Landers have touched down on Venus, Mars, and Saturn's moon, Triton. Numerous spacecraft are currently operational at Mars and Jupiter. However, to Uranus and Neptune, we have sent just one spacecraft, Voyager 2, which spent mere hours near each planet before continuing its journey beyond the solar system. Everything we understand about Neptune from close range, its great dark spot, its winds, its magnetic field, its rings, Triton's geysers, originates from a single flyby on one day in August 1989. We have never orbited Neptune, never deployed a probe into its atmosphere, and never set foot on Triton. If we misinterpret Neptune, its internal structure, heat budget, dynamo, and atmospheric dynamics, we risk misunderstanding the properties of thousands of similar worlds scattered throughout the galaxy. The stakes are not just local, they are cosmic. Several ambitious mission concepts have been proposed to return to Neptune, with the most notable being Neptune Odyssey, a flagship-class orbiter and atmospheric probe crafted by a team at the Johns Hopkins Applied Physics Laboratory. Drawing inspiration from the grand scale of the Cassini mission to Saturn, Neptune Odyssey is slated for launch in the 2030s. It would embark on a journey lasting 12 to 16 years, contingent upon the availability of a gravity assist from Jupiter, before spending 4 years orbiting the Neptune system. Equipped with a comprehensive suite of instruments, it aims to investigate Neptune's atmosphere, interior, magnetic field, rings, and its smaller moons. The mission would conduct numerous close flybys of Triton, mapping its surface, searching for a subsurface ocean, and examining its geysers and atmosphere. Prior to entering orbit, it would deploy a small atmospheric entry probe that would descend into Neptune's atmosphere, gathering data for approximately 37 minutes as it descends to the 10-bar pressure level. Like Cassini, this mission would culminate in a grand finale, navigating through the rings before making a final descent into Neptune's atmosphere. The data returned would revolutionize our understanding of ice giants, Kuiper Belt dwarf planets, and planetary systems as a whole. However, Neptune Odyssey was not selected. The 2023 to 2032 Planetary Science Decadal Survey, the once-a-decade report that outlines priorities for NASA's planetary exploration program, designated a Uranus orbiter and probe as the top priority flagship mission, surpassing Neptune. The reasons for this decision were largely logistical. Uranus is closer, which translates to shorter travel times and reduced fuel requirements. Launch opportunities are more favorable, and the mission architecture is simpler and more cost-effective. For now, Neptune must remain patient. Other concepts are on the table, such as the Trident flyby mission, which aimed to reach Neptune and Triton by 2038 but was not selected. A Chinese proposal for a nuclear electric probe that would orbit Neptune and potentially land on Triton. And the Nautilus concept, a new Frontiers-class Neptune orbiter that could launch in the 2040s and arrive in the 2050s. Yet the timelines are extensive and the distances are immense. A spacecraft launched toward Neptune in the 2030s would not arrive until the late 2040s. The children born in the year of its launch may be entering adulthood by the time it transmits its first images. This illustrates the temporal scale of outer solar system exploration, measured not in months or years, but in decades. Each decade we wait is a decade during which the most prevalent type of planet in the galaxy remains largely unexamined by dedicated spacecraft. There is an urgency woven into these lengthy timelines. Triton's South Pole, where Voyager 2 detected the geysers, is currently basking in sunlight. However, as Neptune orbits the Sun over a period of 164.8 years, the southern hemisphere will eventually be shrouded in darkness. Major plumes will continue to be illuminated until around 2060, but after that, the chance to observe them will not arise for over a century. Each year of delay constricts the observational window. Moreover, there exists a deeper urgency, one that transcends mere timelines or launch dates, addressing our intrinsic curiosity. The human species has roamed the Earth for approximately 300,000 years. For nearly all of that time, Neptune remained hidden, a silent sentinel in the outer darkness, orbiting patiently while safeguarding its secrets. We have known of its existence for less than 200 years and have glimpsed it up close only once. The chasm between what we know and what we could discover is vast, and it widens with each passing year that we do not return. We launched Voyager 2 toward Neptune long before the internet became a part of our daily lives. The scientists who meticulously analyzed its data relied on computers far less powerful than a smartphone we carry today. The stunning images that unveiled Neptune's great dark spot, Triton's geysers, and the solar system's swiftest winds were processed using techniques that now seem almost archaic. Just imagine what revelations await us with today's advanced instruments, cutting-edge cameras, and modern spectrometers, tools that are 1,000 times more sensitive than those aboard Voyager. The truth is, we don't know, and that uncertainty is precisely why we must embark on this journey. Now let's take a step back from the specifics, the wind speeds, magnetic field readings, and orbital dynamics, and ponder the significance of Neptune. Here is a planet that originated in the wrong region and journeyed to its current position through a tumultuous gravitational ballet that reshaped the outer solar system. A planet whose arrival at 30 astronomical units gave birth to the Kuiper Belt as we know it, ensnaring some celestial bodies, scattering others, and flinging the majority into the vastness of interstellar space. A planet that captured a world from the Kuiper Belt, Triton, and in doing so obliterated its own original system of moons. A planet whose interior may rain diamonds through layers of hot, electrically conductive ice, generating a magnetic field so distorted that it defies comparison with any other planet we've studied. A planet where the fastest winds in the solar system sweep across an atmosphere so frigid and deprived of sunlight that no one anticipated weather could even exist there. Neptune defies easy categorization. It is neither a gas giant nor a terrestrial planet. It is something entirely different, an ice giant, a category of planet that we are just beginning to comprehend, and which turns out to be the most prevalent type of planet in the galaxy. Our solar system's most overlooked planet is, in the grand cosmic scheme, the most representative, and perhaps therein lies the profound lesson Neptune imparts. The solar system does not owe us simplicity. It does not arrange itself for our convenience or conform to our expectations. For centuries, we believed that planets formed in their current orbits, that the outer solar system was cold and tranquil, and that distance from the Sun equated to stillness. Neptune shattered those assumptions. It formed in a different location. It migrated. It destroyed and rebuilt. It churns with storms, fueled not by the Sun, but by its own internal heat. It conceals exotic chemistry within its mantle and a captured ocean world in its orbit. There's something humbling in this reality. We reside on a small, rocky planet in the inner solar system, a warm, vibrant place where water flows in liquid form, where the Sun reigns supreme in the sky, and where weather is driven by solar energy. We often project our experiences outward, assuming that the rest of the solar system follows the same rules. Neptune serves as the correction. It reveals that planets can generate their own weather from internal heat, that magnetic fields can be wildly asymmetric yet still function effectively. That ice can become electrically conductive. That carbon can rain down as diamonds through fluids hot enough to melt lead. That a moon can orbit in reverse, harboring a hidden ocean because it was ripped from its birthplace by the gravity of a world that was itself an intruder. The universe is not obligated to conform to our understanding. It operates under its own laws, which we can uncover but not dictate. Neptune's peculiarities are not a failure of our models. They are an invitation to create better ones. Every time we delve deeper into the mysteries of Neptune, we uncover layers of strangeness, complexity, and significance that surpass our previous notions. Yet our exploration has barely scratched the surface. Just one spacecraft, a single flyby, and a handful of hours of data collected back in 1989. Everything else, images from Hubble, observations from Earth, laboratory simulations of diamond rain, serves as a distant echo, pieced together from a planet that reveals its secrets only reluctantly, like a message inscribed in a language we are still learning to decipher. The solar system is not a static museum of celestial objects. It is a vibrant, dynamic tapestry woven through migration, collision, capture, and gravitational sculpting over billions of years. Neptune stands as a testament to this truth. The planet that seems out of place is, in fact, the key to understanding why every other body occupies its specific location. Its position is no mere coincidence. It is the result of formation, migration, chaos, and the relentless passage of time. And there, 4.5 billion kilometers from the Sun, in a realm of perpetual twilight where temperatures never rise above -200 degrees, Neptune persists in its languid orbit. A single year on Neptune, a solitary journey around the Sun, spans 164.8 Earth years. Since its discovery in 1846, it has barely completed one full orbit, finishing its first complete revolution only in 2011. The planet, identified through mathematical predictions during the age of sailing ships, had yet to return to its original vantage point before the era of smartphones dawned. With an axial tilt of approximately 28 degrees, similar to that of Earth, Neptune experiences seasons. However, each season endures for over 40 Earth years. A Neptunian summer outlasts the reign of most earthly dynasties. A child born in Neptunian spring would grow old before autumn graced the planet. These seasonal changes, though subtle at such immense distances from the Sun, have been detected by the Hubble Space Telescope. Cloud patterns shift, the brightness of the hemispheres fluctuates, and the atmosphere responds to the gradually changing angle of solar illumination. Even at 4.5 billion kilometers, the Sun's influence is palpable, albeit hushed. The planet moves with a patience that renders human civilization a fleeting thought. Its azure atmosphere churns with unseen storms. Its magnetic field sweeps through the void at peculiar angles, generated by exotic ice that has never felt the touch of human hands. Deep within its mantle, diamonds may be cascading through fluids hotter than lava, settling around a core of rock and metal the size of Earth itself. And Triton, the captured moon, orbits in reverse through the darkness, its surface cracking and reshaping, its geysers silently erupting, while a hidden ocean lies beneath kilometers of ice, waiting for someone, someday, to come searching. We discovered Neptune because Uranus was behaving unexpectedly. A wobble, a deviation, a whisper of gravitational influence from something unseen. From that whisper, two mathematicians, working independently in different countries, unaware of each other's efforts, crafted a prediction so precise that the planet was located within hours of the initial search. This moment remains one of the most exquisite in the annals of human thought. It reassures us that the universe, despite its vastness and oddities, is not beyond our grasp. We can listen, we can calculate, we can uncover what lies hidden. Yet, finding Neptune was merely the prologue. Truly understanding it will take centuries. and we find ourselves still in the opening chapter. Neptune is a quiet sentinel of the cosmos. It doesn't dazzle with a brilliant glow in the night sky, nor can it be spotted without the aid of a telescope. It exists in a realm that feels distant from our immediate grasp, far beyond the fleeting whims of political ambition and outside the common perceptions of our solar system. Yet it is undeniably present. It has always been there, long before we laid eyes on it, before we bestowed a name upon it, even before the elegance of mathematics confirmed its existence from afar. A cerulean orb on the fringes of the void, patient and profound, it harbours mysteries that we have only just begun to explore. And as we attune our senses to its whispers, it unveils its wonders.